Hi everyone, my name is Sílvia, and today I'll be talking about reconciling predictive multiplicity in practice, which I think is a nice continuation to what Shamik has presented in this session. So I'll be telling you about the reconcile algorithm, which is the regional way of reconciling predictions that I'll be discussing, and then we'll go into what we have done with the reconcile algorithm. So let's start with the problem that we're trying to study here, which is the model multiplicity problem. There was a wonderful tutorial on Monday discussing this issue, but the central idea is this one. Usually when we do machine learning, we always think that we fit a model f to the data, and then we predict f of x for every point. In the past couple of years, it has been a growing realization that there is not one single model f, right? We can have a class of competing models, and by competing, I mean of similar accuracy, that all do pretty well, but they still disagree on individual predictions, right? And this is not necessarily a problem. As the line of less discriminatory algorithm shows, if we have a class, we have flexibility, and we can impose other constraints, but there's two very glaring questions that appear once we realize that this is a thing. First of all, if we do have to choose a model to deploy, then how do we do so? And second of all, even if we want to keep the class for flexibility, then we still would like to measure how much disagreement there is within a class. A couple of years ago, Ruth, Tolbert, and Weinstein proposed an algorithm called the Reconcile algorithm, which was trying to give a way of answering the question of what do we do when we get two models that disagree on the predictions. And for that algorithm, they don't even need to be similarly accurate. To be very clear, because I think that's a source of confusion, we assume there's a base optimal. Okay, there is an f star that does predict the correct value for every x. This is usually called the individual probabilities. So think of like weather forecasting, or when we're trying to predict the probability that someone has an illness. So we don't actually observe the f star. We observe usually the Boolean outcomes. But our goal is to build a model f for f star, right? And usually the way we measure how good a model is we take the Brier score, or squared loss, to compare how well, so the accuracy, right, how well the model is doing. The key insight from the Reconcile original paper is that because there is an f star, if two models disagree substantially, well, this can't be. Someone has to be more wrong than the other one. And so if we have data to reconcile from, we can falsify one of the two models, or the two models, but then also, most importantly, we can use the disagreement region to update the models in a way that we only improve their Brier score. So I won't have time to go into the details of the algorithm, but I'll try to give you the gist of it. So you take two models, f1, f2, and two parameters, alpha, epsilon. Epsilon is telling you how much disagreement you count between the models. So I'm only going to take the point where f1 and f2, the predictions disagree by more than epsilon. And alpha is the maximum size of disagreement that you're willing to tolerate. So you take this set, u epsilon, which is a set of points where the two models disagree, and turns out that you can take a gradient step using this region and update either one of the models with that patching step. And you can show by a potential argument that every step can only improve the Brier score of the model that you're patching. Okay, so Reconcile is an iterative algorithm. And at every step, we update one of the two models until they do not disagree. And for those of you who have seen the multi-calibration literature, it's kind of essentially the same algorithm where you find a weakness and then you update using a gradient step. And so you can see it's a form of boosting. And so you keep going until the disagreement region has size less than alpha. And in the original paper, theoretically, they show that the algorithm converges quickly because, I mean, it could be going on forever. Second of all, that at every step, you can only improve the accuracy of the models, and that by the end, the models essentially agree everywhere. So the key takeaway of Reconcile is that we can resolve the multiplicity problem. Again, this obviously does not solve the literature because we do assume here that there is a ground truth and that the people building the models get data from the true distribution, that you have data to reconcile with, and that you might exit the hypothesis class. So there's some interesting things to say about how it relates to the Rashomon set line of work. An important note is that Reconcile is model agnostic. It doesn't matter how you trained F1 and F2. We're only working with the predictions. OK, so we found this algorithm really interesting, and so we wanted to see how to use it in practice, things came out by actually using it, and to extend it in various contexts, and especially we wanted to place it more in the model multiplicity literature because the original paper didn't discuss it as much. So first, let's just implement Reconcile. You can check the code in our paper. We use the usual suspects for the data sets, and we just want to see how it's performing in practice. To create the pairs F1, F2, where you can think the class of competing models, there's several things you can do. Shamik also mentioned many techniques. Basically, we just want to get models that have comparable accuracy, but that disagree significantly. So we can train different classifiers, we can train with different subsets of the data, subsets of features, and so on. Once we have the models, we run the reconcile algorithm, and we see that, I mean, clearly the theorem works in practice, but it's interesting to see how it does. So here on the left, it's a bit blurry, but you see we're plotting the size of the disagreement region for every data set. Every data set is a box. Blue is before reconcile, red is after reconcile. So disagreement area basically drops to 0. And in the right, you see the Breyer score, or MSE, of the models before blue, after red, running reconcile. So they come to an agreement, and we have only improved the accuracy. And actually, it reconciles really quickly. So when we compare the theoretical upper bound with the actual number of rounds, drastic difference. So it's a very loose bound. So we found it to be really efficient in practice. It was only like 15 iterations. Good, so now let's think more about how this relates to the model multiplicity literature. I mentioned at the beginning the 2 main goals that we would like to have. One is how do we actually choose a model if we have to? And second is let's try to create not too many disagreements in the class, even though we want to keep a class for flexibility. So in the paper, we show how to use reconcile for both goals. So for the first goal, there's different things we could do, but the Black, Ragavan, and Barocca's paper proposed 3 ways for choosing a model. You can take the majority vote, or you can basically choose at random. Right? What are these methods trying to do? They're really trying to optimize for non-arbitrariness. But this leads to a very interesting question, which Shamik also mentioned, which is, if we do propose a method for choosing a single model, how do we compare across different ways for doing so? Because the Breyer score isn't really the good metric here. They all have good accuracy. And so Shamik was saying, even if it's like 0.1% more, it's not that satisfying as an answer. But still, to use reconcile, we basically use reconcile sequentially on the model class. Okay, so we go linearly through the models, and we reconcile each pair until we find a single model. And that's the model we output for the class. Okay? And then we compare it with, say, take the majority vote, and we see that sequential reconcile also gets a good MSE by the end, as one would expect. The second goal is to measure the predictive multiplicity within the class, and there have been several metrics proposed for doing so. And so in this case, we use reconcile for creating a new class, M prime from M, so we don't stick to a single model, we just reconcile them in different ways and create a new class, and you can check the tables in the paper, but what we see is that the new class M prime, when we measure the disagreement within the class, we have drastically reduced it. So you can still keep a class, but we have removed all the probably wrong disagreement that was in that class. Great, but as we were saying, for the first goal of choosing a single model M, the Breyer score as a metric is not really, as I was saying, satisfying. So we were thinking, what are the benefits to having a reconciliation procedure as opposed to, say, majority vote, right? Just like mode or mean aggregation. In democratic sense, it's kind of like we gather the people, when we have to vote for a proposal, we gather the people into a room and we make them speak rather than just like taking a vote, right? So there has to be something good about this. And we formalized 2 ways of thinking about this. One is robustness and the other one is fairness. So first for robustness, the idea is that I told you that the reconcile procedure never makes the accuracy be worse, right? And by the end, the models do not disagree, which means that if you start with a bad model in terms of accuracy and a good model, by the end, the good model prevails, right? Because the accuracy did not go down. So if we generalize this, that means that we have a class of models and we reconcile in the sequential manner. Even if you have some bad models in EB, they will not override the good models throughout the process, which I think is a very useful property if we think of ensembling methods. And so we prove this in the paper, and then we run an experiment where we start with a set, and then we sequentially transform every model into set into just a random model. So it just predicts randomly everywhere. So let's look at the first row. We do it for all the data sets. Let's look at adult. The first row, so the x-axis is adding more and more random models. Okay, so by the end, so that's why it's all red in the end, it's all random. All the models are random. For the first row, the way we ensemble them is by taking the majority vote. The second row, we apply sequential reconcile. So you'll see that sequential reconcile, even though we keep adding random models, because there is one good model still until the very end, the accuracy doesn't drop. Whereas for the majority vote, even with 3 models, you already drop. Sorry, I'll take into questions because, oh, yes.
So when you're introducing models, are you first reconciling the 2 models and then taking the output of that one and reconciling it to the next one? Or are you doing something
with k models at a time.
Okay.
Yes, yeah, thank you. Great, so this is about the robustness. And the second way in which we thought about how do we think about the benefits of reconciliation is through fairness. So similarly, if, even when you have fairness as accuracy, many problems arise, right? You could have subgroups, you could have be accurate globally, but in a subgroup have bad accuracy, right? And so the idea here is that if I reconcile two models and I have a subgroup P, if one is doing very well on that minority group and the other one is not, reconciliation should also preserve that because it always preserves accuracy. And so what we did is take the data sets, now we define two subgroups, a majority and a minority, and then for one of the groups, we assign random predictions to the minority group, right? So it's doing very badly on a subgroup. And then we reconcile them. And again, I think it's a very useful trait. So the first two columns are what's happening, the accuracy over the majority groups, okay, for first model, second model. The third and fourth are for the minority groups. So if you look at the adult data, the red 0.33 is like the bad model. So it's doing really badly on the minority group. But after we reconcile it, because the other model is doing well on the minority group, the reconciled model has good accuracy in the minority group. And so we see it as a fairness guarantee because, it's really typical in practice that someone might have good data for a minority group, the other person does not. And so when we ensemble those, we want to preserve that. And we also prove a theorem that says that this happens in theory. Okay, so I'm out of time, but I'll just tell you, for those who like causal inference, that you can similarly try to reconcile like Kate predictors instead of just in the usual prediction setting. And so we also run experiments with, in the causal setting, where we extend the reconcile algorithm to Kate predictors. And a similar thing occurs where we reduce the disagreement, and we can only improve the accuracy of the predictions. And this is a diagram summarizing the experiments that you can see in the paper. But the takeaway is that reconcile we found it to be a very useful and efficient model-agnostic method for resolving predictive multiplicity in practice, converges quickly. We have compared it now to the methods and kind of questions going on in the model multiplicity literature. I think there's many other things we can try to think beyond robustness and fairness into what this reconciliation procedure, what the benefits of this really are. And we can extend it to causal inference and other settings. And I think the model multiplicity problem is really fascinating. I also encourage you to check the tutorial on Monday. And thank you very much for your attention.